Okay, so we're done with the dimensionality reduction portion of the class, or at least the JL portion of the class. And now we're going to move into something else, although JL will be relevant for this problem too. So the next few lectures, we'll do large-scale linear algebra. Okay. And today we're going to focus on approximate matrix multiplication. Okay. So I'm imagining that we're given two matrices A. A is an n by D matrix, and B is an n by P matrix. And think of n as being big. N is much bigger than both D and P. So these matrices look something like this. Okay, and what we want to do is we want to compute the matrix product A transpose B. Okay. So the straightforward algorithm takes time, something like O of NDP, just 4 loops, right? There are fancier algorithms. So one thing you could do is you could write, let's just, alternatively, you could do the following. You could say A transpose looks something like this. This is the big dimension. And then here's B. Okay. So maybe we should figure out. So he took over scribing because since you weren't here, is that? So okay, so one of you is scribing at it. Well, you guys can. Who is the one scribing, or? Who's you're scribing? Okay. So let's say this thing is P, and this thing here is D. Right. So one thing you could do is just kind of break this up into D by D blocks. Let's just pretend that D divides N. If it doesn't, just pad the matrix with some zeros, okay, with some extra rows that are 0. And also assume D divides P, again, padding by zeros. And you could then kind of, these are all D. You could multiply kind of block by block, right? So if you look at A transpose B is also kind of, you can break up the output matrix into D by D blocks, and each block is a sum of, like, for example, so this matrix, the output matrix would be D by P. And you can break that up into blocks that are D by D. And then this here is basically this times that plus this times that plus this times that plus this times that, right? So you reduce it to a bunch of square matrix multiplications, and you can use fast square matrix multiplication, which each one takes something like d to the omega time. Omega is the exponent of fast matrix multiplication. Okay, so we know, for example, that omega is less than log base 2 of 7. That's Strawson. And there have been a bunch of improvements. So kind of one notable one is omega is less than something like 2.375 or 2.376. This is Coppersmith and Winograd. And then there were improvements by others as well afterwards. So 2.374, omega is less than, I think, 2.373. And then omega is less than, well, let me be more specific, 3.728.642, and then 2.3728639. So these two digits over here got improved. Okay, so this is Stothers. This is Vasilevska-Williams. So these two were done independently. And there's here Legal. Okay, so you could do these things. Kind of ideally, you want to make it to be 2, right? The output has size d squared. You could also reduce to a bunch of rectangular matrix multiplications. What does that mean? So you can multiply let's say an r by r to the alpha by r to the alpha by r in, let's say, O of, well, n to the 2 plus the log 1, let's say, n to the 2, r plus 2 to the log 1. So the question is kind of what's the biggest r, what's the biggest alpha for which you can do this? And you can get alpha to be something that's at least 0.30298. This is also due to Legal. I mean, there's more history here as well. There was a previous bound by Coppersmith, but this is the best bound known. So you can reduce your problem to these fast matrix multiplication problems, or problems. But you could also kind of go a different route. And notice all of these algorithms I mentioned before, just now, are exact computation, right? You actually want A transpose B exactly. So today, suppose we're willing to settle for approximation, which is what we've been doing a lot in this class, right? So settle for computing some C, matrix C, in RD by P, such that A transpose B minus A transpose B minus C, some norm. Okay, suppose I'm willing to settle for that kind of thing, for some norm, so some X norm. And the question is, can we do this faster than these approaches? Okay. So the first, so we're going to discuss this today. And the first method that we're going to look at is using, is getting Frobenius norm error. Frobenius norm. Remember that the Frobenius norm of a matrix is the sum over all ij, mij squared, square root. So treat the matrix like a vector and take its L2 norm. Okay. So Frobenius error. We're we're going to look at two different approaches. And we're going to look at another form of error after this, and they're also going to be similarly two different similar looking approaches. So two approaches. So the first one, which came first historically as well, is sampling. So what are we sampling? You'll see in a second. This approach, as I'm going to describe it, is due to, let me make sure, I think it's Dranais, Mahoney, and Muthukrishnan. Oh, Dranais, Kannan, and Mahoney. So Dranais, Kannan. This is two N's. And Mahoney. This is Psi Compo 6. Okay. And then we're also going to look at kind of a JL-like approach. Or some, yeah, you'll see what I mean in a second. So that's due to Charlotte. Okay. So what do I mean by sampling? Say the rows of these matrices A and B, let me give them names. So let's say the first row is A1 up to AN, and these rows are B1 up to BN. I guess transpose. So for me, like all vectors are column vectors. Okay. So in general, whenever you have, you can verify this. Whenever you have a matrix product, so A transpose B is exactly the same thing as the sum k goes from 1 to n of AK BK transpose. Okay. So what are we going to? So it's a sum of n outer products. So when I say sampling, what do I mean? I mean we're going to sample some n's from this outer product. Okay. So we're going to have C be pi A transpose pi B. Okay. Where pi is going to be an m by n matrix. Okay. And and what we're going to do here is we're going to write pi is going to be a sampling matrix. What do I mean by a sampling matrix? I mean each row has a 1 in a random location. Okay. And this is not going to be exactly right. So let me write, so let's say with scaling. Let me tell you what that scaling is. Well, actually, the pi's, yeah, so good. So this is the scaling. So pi ij, so let's look at the rows that are, let's call them pi 1 up to pi m. So the rows pi I are, let's call pi t, are independent across t. And let me say that pi t is equal to EI with probability EI over square root MP I with probability proportional to, proportional to AI times BI. proportional to the product of the L2 norms. Okay, so I claim that if you do this, notice that this is not, the sampling probabilities depend on the input matrices. This is not oblivious to the input, unlike, say, JL, for example. Okay. So you'll do some pre-processing, compute all the row norms, and then sample according to these row norms. And the row norms you can compute quickly. You just kind of scan the matrix, right? The two matrices. So now let's write C, this matrix C. C is going to be equal to the sum, kind of k goes from 1 to n, m, 1 over m, a kt, b kt, transpose over pkt. So kt, you're basically, there are m rows here. There are m samples that you're sampling from this sum of outer products. And kt is the row you sampled in the tth row of pi.
So you mean that t goes from 1
Oh, thanks.
What is pi?
So with probability pi, right, so the probability that you sample row I is pi. And let me call this thing here well, actually, right. Oh, yeah. Okay.
So what do you mean by with probability proportional to that? Any?
Well, I mean, probabilities should sum to 1, right?
Yeah.
So what I mean is the probability that you sample row I is that over the sum over all j of that.
Okay, makes sense.
Yeah. Okay. So the first thing is, why do I scale by, why do I want to scale by this? Basically, kind of claim, this is an easy claim. The expectation of C is equal to A transpose B. And the proof is just linearity of expectation, since the expectation of ZT is equal to A transpose B over M, right?
That expectations over the randomness of either.
This is over pi.
Okay. So t might be any of the rows.
Yeah, since kind of for all t between 1 and m, this is true. Right, so just use linear expectation. Okay, so this is, that's why I divided by pk, just to get an unbiased estimator. So now I want to argue that this thing actually gives me something good with good probability. Okay, so claim if, let's say, if m is at least 1 over epsilon squared delta, then the probability that A transpose B minus pi A transpose pi B, Frobenius norm, is bigger than, let's say, epsilon times Frobenius A Frobenius B, is at most delta. Right? So let's prove that. Well, we know that this probability is by Markov's inequality. First of all, I'm going to raise both sides. I'm just going to square both sides. Okay. This probability is at most 1 over epsilon squared Frobenius norm squared times Frobenius norm squared of B times the expectation of this Frobenius norm squared. Right? This is Markov. So that's, we just need to understand that, and that's where our choice of pK is going to come into play. I mean, so far, to get an unbiased estimator, the pKs could have been anything, right? As long as none of them were 0. But then this variance calculation is going to depend on the pKs, and that's, you're going to see now why we chose pKs the way we did. So first of all, let me just say without loss of generality, A Frobenius norm equals B Frobenius norm equals 1. Okay. Because you could have just you could just scale, pretend that A was actually A over its Frobenius norm and B was actually B over its Frobenius norm, right? And then just carry that out for this. And since pi is linear, you can put the scaling back at the end. Okay. So we can write A transpose B minus C is a sum over T, goes from 1 to m, of ZT minus expectation ZT. Right. So this implies, so expectation of A transpose B minus C Frobenius norm squared. Well, the Frobenius norm squared is the sum over all ij of the entry squared. So this is equal to the sum over all ij. And then sum over t, or expectation, sum over t from 1 to n. Let me not do this. Expectation over pi of sum over t from 1 to m, zt minus expectation zt ij squared. Okay. And this is just equal to sum over all ij of the variance of sum over t zt ij. Actually, is this what I want to say? I think this is right. And by independence of the zt, this is equal to sum over all ij of sum over t of the variance of zt ij. And all these zt's are identically distributed. So this is just m times the sum over all ij of the variance of kind of zij, right? Where zij is kind of just one of, z is one of them. Okay. So let's calculate this. Well, zij is equal to sum k goes from 1 to n. Let me write it as eta k over pk, ak bk transpose ij. So AK was the kth row, so AKI is, let's say, AKI, BKJ. Okay, where eta k is equal to 1 if tth row of pi samples row k. So only one of the eta k's is 1, and all the rest are 0, right? Eta k is just an indicator of kind of which row did we actually sample from the tth row of pi. Yeah, there is 1 over missing. Okay. And now notice that the variance of Zij is at most the expectation of Zij squared. And if you square this thing, you're going to have, if you expand the square, you're going to have some terms that chose the same k twice, right? And then you're going to have some terms that chose a different k in the first and the first and the second, kind of the off diagonals. Okay. In the off diagonals, notice that eta k times eta k prime is always 0, because you only ever sampled one guy. You're only sampling one guy. So the diagonal terms are the ones that matter. So this is equal to 1 over m squared times a sum over k goes from 1 to n. Then you have the expectation of eta k over pk squared times aki bkj squared. And then the expectation of eta k is pk. So this cancels. Okay. And then, remember, pk, this is equal to, I claim, 1 over m squared times okay, good. So let me leave it like that. So this implies that, going back up there, the expectation of A transpose B minus C Frobenius norm squared is at most, so there's an m over m squared, at most 1 over m. Okay. And then we have a sum over ij of this. If you sum over ij of these, right, then so times a sum over ij, sum over k from 1 to n. Well, let me write it like this. Sum over k from 1 to n. Sum over ij, aki squared bkj squared. There's a 1 over pk here. Okay. You look like you're.
I'm trying to understand why it's not the case that only one of the eta k's is 1. Like Zij would also generally is like Z1 ij, right?
But what are you trying to understand? Why only one eta k is 1?
Yeah. Why it's not the case that only one eta k is 1?
It is the case that only one eta k is 1. Only one eta k is 1. Right? What is zt? Zt is corresponding to
I see. So I just
to our tth outer sample. Zt corresponds to the tth outer product that we sampled.
right at the ij coordinate.
Right.
So I'm thinking of it as like Z1 ij. So so I'm saying that only one eta k is 1.
Yeah. So you can think of this. This is z1 ij. Is that what you?
Yeah, exactly.
That's right.
I see.
Z for me was a generic one of the z's.
I see, and that's why you're saying we use. Okay, never mind. I'm with you.
You believe me? Okay. And this here, this sum over ij of this thingy is just equal to ak L2 norm squared times bk L2 norm squared. Right? If you just expand out this product, you get exactly that. And then now remember what pk is. pk is ak times bk over the sum of all of them. Okay. So this thingy is equal to, by definition of pk, 1 over m, sum k goes from 1 to n, ak L2 norm times bk L2 norm squared. Right? This is just because pk is equal to ak bk over the sum over all j of aj, bj. That's what I meant by when I said proportional to this. And then I use Cauchy-Schwarz. This thing is at most 1 over m times the sum k equals 1 to n ak squared times the sum k goes from 1 to n bk squared. Okay. Actually, I said with all subgenerality those Frobenius norms are 1. I never really even made use of that assumption. I didn't need to say that. And this is just equal to the Frobenius norm squared of A, and this is equal to the Frobenius norm squared of B. Right? So going back here, let me call this thing star, the tail bound we actually care about. By Markov over there, we have that star is at most, well, the Frobenius norm squared of A and Frobenius norm squared of B cancel, and that this is at most, or well, strictly less than 1 over epsilon squared m. And I chose m to be bigger than 1 over epsilon squared delta, so this is less than delta. Okay. So that's it. Okay, and so now notice, originally to multiply A transpose B, it took me NDP time, right, just using for loops, or I could have used fast matrix multiplication. Now it's taking me, instead of NDP, it's taking me MDP. But think of m as like a constant, right? Epsilon and delta are some constants. So this is much faster. Of course, you also have to take into consideration the time it takes to multiply pi times A, right? But that's also really fast because pi is just a sampling matrix. It's really sparse, right? So you can sample rows in like sublinear time. Okay. Okay, good. So that's all I wanted to say about that. Now, one thing might strike you here, which, you know, coming from streaming land and dimensionality reduction, which is, right, this unfortunate dependence on delta, right? Usually we like to get log 1 over delta, right? I want to succeed with probability, you know, 0.999999, and I don't want my running time to scale like then 1 over a million or whatever, or by million. Okay. So, question: how can we modify this so that we get a log 1 over delta instead of a 1 over delta, right? And the usual approach when we were trying to compute numbers, the usual thing we did was we set that delta to be something like 1/10, right? And then we repeated this whole scheme log 1 over delta times and took the median, right? And that worked by a turn-off bound. So it's like a median of the basic estimator. This is even back from lecture 1 or 2. So there's a problem here, which is what are we taking a median of? These are matrices. These are not numbers. I don't know what median means anymore. Okay? So, but there was a trick. So improving runtime to depend on log 1 over delta instead of 1 over delta. So we're going to use a trick that's due to Clarkson and Woodruff. This is from Stock 2009. Okay, which is set R to be something like, you know, log 1 over delta. compute, C1, CR as before, each with failure probability you know, 1 over 10. Okay. So what do I know now? Well, again, by a turnoff bound, I know that 2/3 of these C matrices actually work, right? So that's just by writing, using the usual turnoff trick. Let xi be an indicator random variable for the event that ci worked, that it got small error. And by turnoff, you know that 2/3 of the ci are good with probability 1 minus delta. So now the question is just, how do we figure out which of the c's? We just need one c which is good now. Before, the way we did that was we took the median. Okay. One thing you could do is just check, right? We know by Chernoff that at least 2/3 of the CI give low error. Even say at most epsilon over 4 Frobenius A, Frobenius B. Okay. Imagine the old epsilon was actually epsilon over 4. Okay, so check which one is good. For I goes from 1 to R, if A transpose B minus CI is at most epsilon over 4 times, whatever, return CI. This would work, right? This is correct. But what's wrong with this? I need to actually compute A transpose B, right? And that's exactly what I don't want to do. So instead, the clever trick is going to be as follows. Instead, what we're going to do is for I goes from 1 to R. Okay. And then let's say I'm going to initialize some counter to be 0. For J goes from 1 to R. If CI minus CJ for Frobenius norm is at most epsilon over 2 times the product, then counter and gets incremented. Okay, and then what I'll say is, if the counter is at least R over 2, then I'll return I. Okay, so that's what we're actually going to do. And now I don't need to ever actually compute A transpose B. Okay, why does that work? Well, the reason is pretty simple. So the analysis number of good I is at least 2R over 3. We said, right? Or actually, we just need that it's bigger than R over 2. If I is good, then when I say good, I just mean the error is small. Then for good J, we have triangle inequality. Ci minus Cj Frobenius norm is at most A transpose B minus Ci plus A transpose B minus Cj, which this is at most epsilon over 4. Did I really need epsilon over 4? Maybe I could have gotten away with epsilon over 2. But anyway, this is at most epsilon over 2 times whatever plus epsilon over 2 times whatever, 4. So that's at most epsilon over 2 times Frobenius A, Frobenius B. Okay, so whenever we enter the main loop with a good I, we will definitely return that I. Now the question is, what if before we reach that good I, maybe some bad I fools us? Can that happen? Okay. And I claim that can't happen either by triangle inequality. And the reason is, if he's close to more than half of the R's, or if he's close to more than half of the CJs, well, one of those CJs had to have been good, right? Because more than half of the CJs are good. The majority of CJs are good. So he's close to some good CJ. But if he's close to some good CJ, then he's close to A transpose B by triangle inequality, right? Because his distance to A transpose B is at most his distance to CJ plus the distance from CJ to A transpose B. Both of those are small. So by triangle inequality, he's close to A transpose B. So, yeah, sorry? Yeah, I did need epsilon over, well, I could have probably done something a little better. Because now I'm getting 3 epsilon over 4. Right? So his distance, by triangle inequality, it's his distance to this guy, which is epsilon over 2, plus that guy's distance to A transpose B, which is epsilon over 4. And I probably could have made these epsilon over 2. Yeah, whatever. Okay? Changes things by a constant. So that's the end. Okay, that's the analysis. So questions about this? Okay. Yeah.
So maybe more high level question.
Yeah.
So if you want to, like this scheme, this sampling scheme reminded me of trying to approximate the best theorem of a given matrix. So in that case, you're sampling each row proportional to the length of that row, right?
Yeah.
So here, it's not the same problem, but it somehow brought that.
Right. So when you yeah, so
I was wondering about the intuition that was like.
So yeah, we're going to talk about lower rank approximation probably next. We'll probably get there by next week. There are also sampling ways of doing that. The real thing that matters a lot here is what error guarantee you want. Okay, so we want this Frobenius norm error guarantee, which is not the strongest form of error guarantee we're going to look at. And for that, all that really matters are the row norms, the L2 norms of the rows. We're going to see another form of approximation, which is a better form of approximation, but then we're going to end up paying more. Pay more in terms of what? Pay more in terms of m. So here, I guess I erased m is basically a constant, right? So we're going to see that if we make m bigger, we can get better notions of approximation. Okay, good. So this says that I good implies will return Ci if loop enters I. And also, we won't return a bad I by the argument I just said verbally. So that's all I want to say about sampling to get Frobenius norm error. Now I want to tell you about kind of the JL approach to get Frobenius norm error, which is going to be oblivious to the input. So this pi actually depended on A and B, right? This one isn't going to depend on A and B. So the JL approach. Okay, so let me first give a definition. Okay. pi, let's say pi is an n by n matrix, satisfies the, we call it the epsilon delta p JL moment property. If the following is true, for all x, so this is the sphere. So for all x, n-dimensional x which have unit norm, we have that the expectation over pi. So I should really say that pi, so there's a probability. So pi is not a fixed matrix. So D, okay, D is a distribution over pi's. So this probability distribution over pi's satisfies this property if, when you take a random matrix from this distribution, so pi is drawn according to this distribution, and you take the expectation of this quantity, pi x L2 norm squared minus 1 to the p, the pth moment of this error, this should be at most epsilon to the p times delta. Right?
What do you mean by a distribution over pi? You mean pi is normal distribution or?
Yeah, so there's a distribution over m by n matrices, okay? And that distribution over m by n matrices satisfies this JL moment property if this expectation is small, where the expectation is taken over a random pi drawn from that distribution. Okay. Examples. So suppose that pi ij is equal to plus minus 1 over root m. Okay. When we analyze the AMS sketch, what we showed is that it has the epsilon delta 2 JL moment property, where m had to be at least what to have this? Okay. I don't, well, if I take, so p is 2 for me right now, right? When we analyzed the AMS sketch, we basically showed it had this property. And what did m need to be to have this property? Right, this was basically a variance calculation. So we're looking at the second moment. And when you're dealing with the second moment, you get something like 1 over epsilon squared delta. Okay. When we did the J, so this is AMS. We also looked at it from JL, when we were analyzing JL, and we showed that we have the epsilon delta. Which moment was relevant for JL? Yeah, log 1 over delta, right? So one way to see that is, well, if you remember how we analyzed JL with Hansen-Wright, we showed that the probability that you deviate by more than epsilon via Hansen-Wright was at most e to the minus epsilon squared m plus e to the minus epsilon m, which is kind of a mix of Gaussian and exponential moments, or Gaussian exponential tail bounds. So by p set 1, problem 1, that corresponds to using the right moment to get the right failure probability. Okay. Actually, I think there was a p set problem on p set 2 maybe that asked you basically to figure out which moment was being used in the moment estimation analysis. Remember we analyzed this algorithm for estimating moments in data streams when the moment was bigger than 2? and we used Bernstein's inequality. And there was one PSET problem that asked, which moment were you really using when you're doing Bernstein? Basically. And again, usually when you're getting failure probability delta out of Bernstein or out of Chernoff, you're really using the log 1 over delta f moment. Okay. And here m could be log 1 over delta over epsilon squared. Another example is the matrix from PSET 1 problem 4, I believe, where each column had a random sign in one location and zeros everywhere else. Right, this is the Thorpe-Jong sketch, which was based on the count sketch. And that, so what JL moment property did it have, and what did M need to be? So let's say epsilon delta, what was P? What moment did you use in PSET 1? If you remember, it was a while ago. But yeah, it was 2. Oh, sorry, it's norm estimation in data streams. It was a faster version of the AMS sketch. Because the AMS sketch, you need this dense sign matrix. It turns out you can just use hashing. And that was, again, a variance calculation. That was the second moment. And M needed to be the same thing. M could be 1 over epsilon squared delta. Okay. Okay. Good. So why did I write down this definition? What's the point of this? So now we have a claim. This is the main theorem of the JL approach. Suppose pi comes from some distribution that has the epsilon delta p JL moment property for some p that's at least 2. Okay. Then I might switch colors now because the yellow chalks are all dying, basically. Okay, then this is equally visible? Very good. Then for all matrices AB with equal number with n rows, pi also has n columns. We have that the probability over pi coming from whatever this distribution that has this property that A transpose B minus pi A transpose pi B is greater than 3 times Frobenius A Frobenius B is at most delta. Okay, it's the same kind of guarantee as with the sampling approach. It's just that we're using this JL moment property instead of sampling. And this has the advantage that it's oblivious to the input. So for example, if A and B are being updated in a data stream, in a turnstile data stream, someone says I want to add or subtract some amount from some entry of A or B, then I can use this approach because it's oblivious to A and B, right? Whereas with the sampling approach, I need to know what the final A and B L2, what the final row norms are to pick the sampling probabilities. And if A and B are changing, then I don't know what to do at the beginning of the stream. Yeah. Yeah, it does, sorry. 3 epsilon. Okay, actually, so this is what, this thing is in my paper with Daniel Kane. pretty simple lemma. I should mention that this 3 epsilon can really be epsilon. This was pointed out to me by this guy, Olivier Zahn. So at some point, I guess in the paper, Daniel and I were just really sloppy with triangle inequalities. But if you really do this properly, you don't actually lose in terms of epsilon. Maybe I'll make that a homework problem. Okay. Yeah, so I'm not. The next homework is going to be released next week because I want you guys to have ample time to focus on picking a good project. So your project proposals are due next Thursday. So then I'll release the next p-set next week. There'll only be 2 more p-sets. Okay, so yeah. Okay, good. So let's prove that. So let's prove this. Notice that the probability that this thingy is bigger than epsilon times this thingy. Okay. By Markov, this is at most 1 over epsilon to the p times the Frobenius thingies to the p times the expectation of that Frobenius norm to the p. This is just Markov. So really it just boils down to bounding that pth moment of the Frobenius norm. Okay, so let's focus on that. Okay, so we just need to bound A transpose B minus pi A transpose pi B, Frobenius norm, p norm. Right? The pth moment is just the p norm to the pth power. Again, A has rows AI, B has rows BI. Okay. So A transpose B actually, let me write it like this. This thing is equal to, notice that this thing is equal to the p over 2 norm squared 1/2. Right? Those are the same. And this is actually why I wanted p to be at least 2, so that the p over 2 norm is actually still a norm. Okay. So this thingy Frobenius norm squared is equal to the sum over all ij of, let me make sure I want to write this. Okay, so actually, let me, yeah, okay, good. So the sum over all ij of AI L2 norm squared times BI L2 norm squared times xij squared. What is xij? Xij is equal to pi AI minus, or dot pi bi minus ai dot bi over the norm of ai. over the norm of bi. Okay. So in general, what is the ijth entry of a matrix? So if you take A transpose B, what is the ijth entry of this? It's the ith row of A dotted with, these should be j's. Now it makes more sense. It's the ith row of A dotted with the jth row of B. So if you're looking at A transpose B minus pi transpose pi B and looking at its ijth entry, right, then it's the ijth entry of this minus the, well, it's the ijth entry of this minus the ijth entry of this. Maybe I should have reversed these, but I'm squaring it, so it doesn't matter. Okay. And I'm dividing by the norm so that these vectors are actually unit norm vectors, but then I'm scaling back by the squared norms. Okay, so I'm actually getting pi ai pi bj minus ai dot bj. Okay. Which implies that if you look at the p over 2 norm of this thingy, okay, then by triangle inequality, this thing is at most sum ij ai squared bj squared times xij squared p over 2 norm. This is just triangle inequality. And we're going to prove a bound on the norm of this guy, right? So this guy is the same for all ij. The bound we're going to prove is the same for all ij. So we can pull this out, and we're left with the sum of ij ai squared bj squared. But what's that? That's just the, yeah.
So for the second dot, is it ai?
This one? This one?
Yeah, the right hand.
Yeah, bj. Yeah. Sorry. So if you pull this guy out, you have the sum of ij ai, else the ith row of a squared, the jth row of b squared. That's just the Frobenius squared of a times the Frobenius squared of b, right? Because if you sum up the squared norms of rows, that's just the Frobenius squared. So this thing here is at most the max over all ij, xij squared p over 2 norm times the Frobenius norm of a squared times the Frobenius norm of b squared. This is not even, well, it's not even Cauchy-Schwarz. It's actually just, yeah, it's actually just equality.
Oh, because it's over ij.
Yeah, it's over all ij. Yeah, it's just equality. That's right. And notice, by the way, kind of I dropped the square root that was out here. Okay? So really, when you put that square root back, you get Frobenius of A times Frobenius of B. Right? So when you look at Markov's inequality, over here, you're going to have Frobenius of A to the P, Frobenius of B to the P, divided by, I didn't write it, Frobenius of A, they cancel. And what you're left with is 1 over e to the p times something. So that now it just comes to kind of what is this bound here. So fix ij, and then write, xij is just equal to what do we say? Pi let me call it pi x dot pi y minus x dot y, where x and y have unit norm, because we scaled ai by its norm and bj by its norm. Right? And notice that, going backwards now, xij squared p over 2 norm is just the same thing as xij p norm squared. This is just equal. So now let's look at the p norm of this thing. Xij p norm. Well, let's look at this thing. Notice that we have x minus y L2 norm squared is equal to x squared plus y squared plus minus 2x dot y, right? Which implies that x dot y is equal to 1/2 x minus y squared minus x squared minus y squared. And we can write something similar for pi x dot pi y. So this implies that xij is equal to 1/2 pi x minus y L2 norm squared minus x minus y L2 norm squared plus, right, these are both 1, by the way, plus pi x L2 norm squared minus 1 plus pi y L2 norm squared minus 1. Okay. And now we're just going to use triangle inequality on the p norm. This implies that xij p norm is at most 1/2 times, let me write what, x minus y L2 norm squared times the p norm of pi x minus y L2 norm squared over x minus y L2 norm squared minus 1 plus the p norm of pi x L2 squared minus 1 plus the p norm of pi y L2 norm squared minus 1. Right, this is triangle inequality. And then I use my definition. I have the JL moment property. So I know the pth moment is at most epsilon to the p times delta. The p norm is just the pth moment to the 1 over p. So this is at most 1/2. Let me pull out 1/2 times epsilon times delta to the 1 over p times x minus y L2 norm squared plus 1 plus 1. I can use triangle inequality on this. X and y each have unit norm, so their difference has norm at most 2. So the squared norm is at most 4. Okay, So 4 plus 1 is 6. Divided by 2 is 3. This is at most, that's where the 3 comes from, 3 epsilon delta to the 1 over p. But if you're a little cleverer, you can get rid of the 3. Good. So what have we just shown? So we showed that the p norm is at most 3 epsilon 1 over p, 3 epsilon delta 1 over p. And what we actually cared about was the p norm squared, because the p norm squared is equal to that thing, right? So this implies that, we call this star. Star is at most Frobenius of A squared times Frobenius of B squared times 9 epsilon squared delta to the 2 over p. I just squared that. Okay. And then now going back to what I actually cared about, I had a, see that what I circled over there, I actually had a 1/2 power. I actually cared about the p over 2 norm to the 1/2 power. Right? And then I'm raising it to the p. That's the pth moment. So the probability that that thingy is bigger than 3 epsilon Frobenius A times Frobenius B is at most, well, 1 over 3 epsilon A F B F to the p times the square root of this to the p, which is delta. Okay. Questions? So maybe, okay, so these are the kind of two standard ways now of getting approximate matrix multiplication. One is the sampling approach, when the other is with Frobenius error, and one is this JL moment property. So now, in the last few minutes, let me introduce what we're going to do next time, which is going to be relevant, for example, for question.
So is it right that the approach right in front of you right now, the yellow?
Yeah. Yeah. Right. You could also do this. You could also do this for that. Set delta to actually be a constant, like a 10th, and then do this kind of median, the matrix median trick.
So both of these approaches give the same parameters, which I guess means that this one is strictly better because it oblivious to the input.
Right. So they both give the same m, at least in terms of theta notation. Yeah. M is 1 over epsilon squared delta. And this one is oblivious to the input. That's right. So yeah, I mean, I guess it depends on your goal. If one of your goals is like, for some reason you care about keeping a sample of your rows, then the other thing is what you want. But in terms of like computationally, as you say, this has the same bound as the other one with the added benefit of being oblivious. I mean, the nice thing about the sampling one is the matrix is really sparse, so you can multiply by pi quickly. But so is this one, right? This matrix is also really sparse. Okay, we're going to look at kind of spectral approximation. So let's say pi A transpose pi b minus A transpose B. This is now the operator norm, is at most epsilon A times B. Without loss of generality, for this A is equal to B. Why is that the case? Because I can always define a matrix M that looks like this. Okay. Over, let's say, over the operator norm. Well, okay, but first of all, let me say, first of all, without loss of generality, the operator norms of A and B are both 1. Again, because you can scale down by the operator norms and then scale back up, pi is linear. And then, given that, without loss of generality, A equals B. And then I can do the M that I just did. So this is AB. First of all, and what I want now is pi M transpose pi M minus M transpose M is at most this. Why is it implied? Why does that imply the thing I actually care about? Notice that M transpose M looks something like this. A transpose A, B transpose B. Or actually, good. Okay, and this is A transpose B, I guess. B transpose A. That's what M transpose M looks like. Notice that, first of all, the operator norm of M is also 1. Why? Because if you look at M times a vector, and let's break the vector up into 2 pieces, x and y, this is equal to ax followed by ay, or by, which implies that m xy L2 norm squared is equal to ax L2 norm squared plus by L2 norm squared. But A has operator norm at most 1, and so does B, or equal to 1. So this is at most x squared plus y squared, which is the squared norm of the original vector xy. Right? So it doesn't blow up norms. Yeah?
How can you put A, B together?
I just mean concatenating the columns.
Yeah, but left and right.
Oh. Oh, right. A and B might have a different. I see what you mean. A and B.
The common connection. They have one of the common.
Yeah, so A and B have the same number of rows, and they have a different number of columns, right? So they have the same number of rows n, but A has D columns and B has P columns. So I just concatenated the columns. Does that answer your question?
Because I thought recessive is like
A and so A and
A has the A to it is equals to B type. I thought that's recessive.
well, remember that we've always been looking at A transpose B.
Yeah. Oh,
So A transpose,
okay.
the number of columns of A transpose equals the number of rows of B, but the number of columns of A transpose is equal to the number of rows of A. So A and B have the same number of rows. Yeah. And maybe we're running out of time. Maybe I'll just say, so, get the error on the right-hand side is the same for both. Whether you have the operator norm of M squared versus the operator norm of AB, it's the same thing. And then you just need to make sure if pi M transpose pi B minus A transpose B, why does that have small operator norm? If pi M transpose pi M minus M transpose M has small operator norm, why does that imply that pi A transpose pi B minus A transpose B has the same bound on the operator norm? I'll leave that to you as an exercise. And let me just say one thing, which is, is this is where we were before. Let me do it here. So we'll get actually something stronger than just that error bound. From now on, A is equal to B. Okay, so let me stop talking about two matrices. Want that for all x, pi ax L2 norm squared is equal to 1 plus or minus epsilon ax L2 norm squared. Okay? So we want pi to preserve the norm of every vector that looks like ax simultaneously. It's a bit stronger than that error guarantee, right? Because if you look at this matrix, pi a transpose pi a minus a transpose a, and look at the operator norm. I mean, this is equal to the sup over x of unit norm of x transpose this matrix x, which is pi ax squared minus ax squared, right? And what that bound would give us is it would say that the difference is at most, that bound would say that this thing is at most epsilon times the sup over all y of ay squared. Right? But what I actually want is I just want this to be at most epsilon times ax squared, right? So next time on Tuesday, we're going to look at how to get this guarantee. Okay? And again, there are going to be two approaches. One is going to be a sampling approach, except we're not going to sample by rho norm squared of A. Okay? We're going to sample by something else. And unfortunately, the number of samples we'll need is not going to be a constant. It's going to depend on D. So remember, A is n by D. It's going to depend on the small dimension. More specifically, it depends on the rank of A. But at least it's less than n. So an n by D matrix will get squashed to a D by D matrix, roughly. And then we'll see there's also a JL kind of approach to also achieving this. Okay. And by the way, such a pi is called a subspace embedding. Let me write this down. Subspace embedding. So pi is a subspace embedding for the column space of A. And we're going to see that that's going to be important for a lot of problems, like speeding up least squares regression and PCA and lots of problems. Okay. So I'll see you all Tuesday. And I hope everyone got the email with project tip suggestions. Okay.